7.3 Logarithmic Functions as Inverses. A logarithm is the inverse of an exponential function. Y equals log base b of x if and only if b to the y power equals x. Let's take a look at that for a moment. Notice this b is this b. That's not a coincidence. This y is this y. And this x is this x. There are some restrictions on a log function, and that is that b has to be greater than 0, so we can't have a base here that's negative. The next restriction is that x has to be greater than 0. And that's because if you take a positive number to any power, you're going to get a positive number. So x will only ever be greater than 0. And b can't be 1. That's because 1 to any power is 1. And so that would not make an exponential function. The most important thing I want you to know about logarithmic functions is that the answer to a log is an exponent. The base of the log, which is the b, is the same as the base of the exponent. The base of the log is the base of the exponent. So we call them both bases. We call this a base, and we call this a base. Now, this next statement can be a little tough for people, but at the very least, you could just remember it. Because because y equals log base b of x, and b to the y equals x, these following two things are true. B to the log base b of a is a, and log base b of b to the a is a. I think this will probably become clearer once we practice some problems, but these are very important identities that you're going to have to remember for the future. They actually come up a lot in calculus, especially this first one, and the students really have trouble remembering that, but it does come up often. And this is just a little restriction on the side here that a has to be greater than 0 for this to be true. So a has to be positive. Okay. We're going to work now on changing an exponential form to a logarithmic form. Now, this is usually pretty foreign to people, but let's just look over here for just a second. You don't have to write this down or anything, but 5 times a equals 15, let's say. So that means a couple of things. That means that a equals 15 divided by 5. It also means that 5 equals 15 divided by a. So this is taking a multiplication equation and changing it into division equations. In this case, either one works. So we're going to use that same concept, but with exponents, and it's going to look a little weird, but this is how it goes. Okay, so 100 equals 10 squared. We know that, of course. So to put this in logarithmic form, and you can look up here for the general form up here. So remember that the answer to a log is an exponent. So the answer to this logarithmic form that I'm about to write is going to be the number 2, because that's the exponent. And the base of the log is the base of the power. So this is going to be log base 10 of something equals 2. Well, who's the only something left? Right, it's 100. So log base 10 of 100 equals 2. So let's look at that again. Log base 10 of 100 equals 2. So that's how you change an exponential form into a logarithmic form. Let's try again. 81 equals 3 to the 4th. So we know we're going to have to start with the magic word log. The base of the exponent is going to be the base of the log. The answer to a log equation is the exponent. And there's only one place for the other number to go, and that's here. So log base 3 of 81 equals 4. All right, let's look at this one. So first we're going to write log. This is the base. The answer to a log is an exponent, and this number only has one place to go. So these are equivalent forms. So this is exponential form, and this is logarithmic form. Just like this is a multiplication equation, but these are division equations. Okay. Let's come down and evaluate some logarithms. Log base 2 of 32. So what you want to do here is you probably want to think about it in terms of exponents until you get good at the logs. Just like when you learned how to divide, and you said, 15 divided by 5 equals, your teacher in 3rd or 4th grade probably said, what number times 5 equals 15? This is the same thing. It just is logs and exponents. So we're going to first say to ourselves, 2 to the something power equals 32. So what we're really doing is we're changing this logarithm equation into an exponential equation because exponents are more familiar to us. So this means 2 to some power equals 32. Okay, does anybody know what power on 2 will give you 32? Well, that is 2 to the 5th. 2 to the 5th is 32. So that means that our little x is 5. Now, you don't really want to leave it as x equals 5 because there was no x in the actual problem. This isn't an equation up here. This is we're just evaluating. So what I did after I got this x equals 5, I just came up here and I wrote equals 5. So similarly, if we had 5, that's not a good example, 50 divided by 10. Now, you could say, okay, well, that's 10 times x equals 50, x equals 5. But this is really what we were trying to do. There's no x here. So really, we should say, just equals 5. Okay, let's look over here. Log base 5 of 125. So first I would say 5 to what power is 125? 5 to what power equals 125? And that's what I wrote. So now you have to come up with the power. What is the power? 5 to what power is 125? 5 to the 5, right? No. 5 to the 5? No, it's 5 to the 3rd. I don't know what happened to me there. Oh, well, what are you going to do? That's supposed to be a 3. Oh, that's too fat. There we go. because 5 times 5 times 5, that's 25 times 5. Yeah, 125. Yeah, okay. Just double checking. Okay, so that means what's under this box, of course, is going to be wrong. But that's okay. We'll just fix it now. It happens, right? Okay, so x is really 3. But remember, x is not really, there is no x here. So log base 5 of 125 is 3. So log base 5 of 125 is 3 because 5 to the third equals 125. Okay, let's come over here. Ooh, there's a fraction. Okay, well, log base 3 of 127. I'm sorry, 1 over 27. Okay, well, let's just start the same way. So 3 to what power equals 1 over 27? So the next thing I would do is I would try to make this fraction not be a fraction anymore. So the next thing I would do is I would change the 1 over 27 to 27 to the negative first power. That way everyone's in terms of a power and there are no fractions. And what can you say about 27? Well, 27 is 3 to the third. So 27 to the negative first should be the same as 3 to the third to the negative 1. And in this step here, we can multiply those exponents because power to a power you multiply. So that would mean 3 to the x would equal 3 to the negative 3. So that means that x has to be negative 3. So log base 3 of 1 over 27 is negative 3. Now, it's a little slow going in the beginning, but as with most things, the more you practice, the better you get at it. Okay, let's try some more. I would really like you to pause the video now and see if you can do this one by yourself. Okay, did you pause the video? I hope that you listened. Okay, so 8 to what power is 32? Well, 8 to the first is 8. 8 to the second is 32. 8 to the second is 64. So that's over 32. What should I do with this one? Well, let's see here. On this one, we changed 125 to 5 to the third. But the other side already said 5. Like these bases, they matched, so that was convenient. Could I make these bases match? Well, what do we know about 32? 32, we know from up here, is 2 to the 5th. So let's try that. We're going to make 32 2 to the 5th. And what do we know about 8? 8 is 2 to something also, isn't it? It's 2 to the 3rd. This is going to be helpful because now I'm going to have it in terms of 2's. So now all of the bases will be 2's. And as we did with the last problem in the 1 over 27, I have power to a power, so I can multiply these exponents and get 2 to the 3x equals 2 to the 5th. So therefore, 3x has to equal 5. So x is 5/3. So that means that log base 8 of 32 is 5/3. Now see, you wouldn't have been able to do that without exponents and logs. Okay, let's try this one. Log base 64 of 1 over 32. I'm going to change it to exponential. So let's see if we can remember. 64 to what power equals 1 over 32? Let's make this fraction into not a fraction. I did a lot at once. Interesting. I wonder why I did that all at once. I'm taking that back. Okay. I'm not even sure I like these steps. Okay, so 1 over 32 is 32 to the negative 1, right? And we just said from the previous problem that 32 is 2 to the 5th. And 2 to the 5th to the negative 1 is 2 to the negative 5. Okay, so let's look at the 64. So I know that 64 is 8 squared. So that must mean that this is 8 to the 2x. So that must be equivalent. And what did we discuss about 8? 8 is 2 to the 3rd. So 2 to the 3rd is 8. And that's 2 to the 2x power. And then I can take these powers and multiply them and get 2 to the 6x. And that's going to equal 2 to the negative 5. And because the bases are both 2's, I can set the exponents equal to each other. 6x equals negative 5. So x equals negative 5/6. And that's the answer to this log. Okay. Log base 4 of 32. So we're going to go with 4 to what power is 32? I don't know. I'm going to change 32 into 2 to the 5th, and I can change the 4 into 2 squared. 2 squared to the x power is 2 to the 2x. And once you have the bases the same, they're both 2, then the exponents have to equal each other. So 2x equals 5. X equals 5 over 2. So log base 4 of 32 equals 5 over 2. I hope that was an okay start to logs. Okay, so what's next here? Next we're going to talk about common logs. A common logarithm is a logarithm with a base of 10. A common logarithm is typically written with no base number at all. A logarithm that has no base number implies that there is like an invisible base of 10. So log base 10 of x equals log of x. So if we don't put a base here, oops, bad. Okay. If we don't put a base here, it's like an invisible 10. You know, just like we have invisible 1s and stuff. Okay, so let's evaluate here. So similar to the previous problems, we have log of 1,000. Okay, so the first thing you want to do is just put a 10 there because it'll help you in the beginning. So 10 to what power equals 1,000? So how many zeros are in 1,000? 3. So that means 10 to the 3rd equals 10 to the x. So 1,000 is 10 to the 3rd. And that means x is 3. So log of 1,000 is 3. Of course, I'm writing out every single step. You don't need to if you don't need to. Okay. Oh, what is this? Okay. So don't forget to put in your little invisible 10. So 10 to what power is this gross number? Well, let's think about what that would be. Remember your scientific notation, you know. 1, 2, 3, 4, 5, 6. This number is small. So that means that this exponent is negative 6. So that equals negative 6. Okay, let's come over here. Log of 10. So the base is 10. So 10 to what power is 10? 1. So log base 10 of 10 is 1, or just log 10 is 1. Okay. Logarithmic scales. So this is like a practical use of logs. Logarithmic scales are used when measurements have a really wide range of values. And some examples here are earthquakes, pH, which measures acidity of a substance like in chemistry, even the coronavirus. So I'm sure you've seen, well, actually, I don't know that, but I have seen some graphs of the number of cases of the coronavirus, that look like this. And I'm sure you've heard flattening the curve. So what they're trying to do is they're trying to get this exponential curve to turn this way and flatten and then come back down. There's so much math involved here. But if you have a graph with, number of new cases, that's usually what it is, and time, it's very hard to tell the number of cases because they go up really fast. So sometimes you'll see a logarithmic scale for this. And if you use a logarithmic scale, it actually looks very linear. And so it's just easier to find the values on a logarithmic graph a logarithmic scaled graph if the numbers have a really, really wide range. So instead of the scale being energy released for earthquakes, or number of hydrogen ions, that's for pH, or number of cases of the coronavirus, it uses the logarithm of those values. Okay, so here's an example of the Richter scale for earthquakes. So on the top here, we have the magnitude. Those are the numbers that we're really familiar with, like a 6.8 magnitude earthquake. But these magnitudes really stand for an amount of energy times 30 to a power. I guess Richter I don't know where he got these numbers, but okay. So the energy released from one magnitude to the next is times 30. So it's not just like a little bit bigger. The difference between a 4.0 earthquake and a 5.0 earthquake is 30 times. That's crazy. Okay. So here's some examples. How many times more intense is an earthquake of magnitude 9.3 than an earthquake of magnitude 8.7? And I'm giving you this formula to convert intensity and magnitude, really magnitude to intensity. But so the log of the intensity of one earthquake over the intensity of another earthquake is equal to the magnitude of the first earthquake minus the magnitude of the second earthquake. This formula will also make more sense in future sections when you learn more about logs. So which one happened first? I don't know, but it's just easier to say that the bigger one is the first earthquake. So log intensity 1 over intensity 2 equals 9.3 minus 8.7. So they're saying that you need to subtract the magnitudes. So that's the first step in determining how much worse one earthquake was than the other. And that's 0.6. And now we have to deal with this. So, what does this mean? But remember that the invisible base on a log is 10. So that means that 10 to the 0.6 power equals the intensity of one earthquake over the other. And they're asking you how many more times intense one is than the other. So they're really asking you right here for a comparison. They're asking you for I1 over I2, even though you might not recognize that at first. But this is a common question that you get asked with logarithms, so it doesn't surprise me to see it. After you see it for a while, you know it's coming. So 10 to the 0.6 power is around 4. It's pretty close to 4. It's like 3.96. So what that means, because that equals I1 over I2, that means that the 9.3 earthquake is 4 times more intense than an 8.7. And it might not seem that way if you just look at those numbers. I mean, 9.3, 8.7, you might think, well, that's just a little bit worse. Well, it's 4 times as bad. So, okay, let's try another one. about we try an 8.0 earthquake versus a 6.8 earthquake? Okay, so first you subtract the magnitudes, and we get 1.2. And then remember, the base on a log is 10. So we say 10 to the 1.2 equals I1 over I2. And this, we're not looking for I1 or I2 individually. We're looking for the comparison. So whatever 10 to the 1.2 is it. That's the answer. So an 8.0 earthquake is about 16 times more intense than a 6.8 because, I don't know why I don't have this written, because 10 to the 1.2 is about 16. 16 times is bad. Yikes. Okay. Now we're going to graph some logs. So let's think about this. Okay, so we're going to graph log base 3 of x. But remember that logs are the inverse of exponentials. So if we have log base 3 of x, the first thing we're actually going to do is we're going to make a table for y equals 3 to the x. That's the inverse of log base 3. These are inverses. I'm actually going to erase that. These are inverses of each other. So we're going to first make a table for y equals 3 to the x, because as we discussed before, exponents are more familiar to us. So for a 3, we can start with our x values of negative 3 to 3. And then remember, when we make our table, we usually start with 0. So 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and 3 to the 3 is 27. And then for the negative exponents, it's the reciprocal of the positive answers. And that's y equals 3 to the x. Now we're going to graph 3 to the x. I know what you're thinking. You're like, it's supposed to be log base 3 of x. Okay, so first we're going to graph this. We'll graph this in green. So 0, 1, 1, 3, 2, 9. We'll skip this one because that one's too big. Negative 1, 1/3. Negative 2, 1/9. Negative 3, 1/27. It's just getting closer to the x-axis. Do your best curve. And remember that there's an asymptote here. Okay, remember how we make the dotted line? Okay, now what do you remember about inverses from last chapter? Inverses are reflections over the line y equals x. So what we can do here is we can sketch in the line y equals x. And we can reflect this green one right over the purple one. So let's zoom in here. Let's look at this point first. That point is going to be here at 1, 0. This point will be over here at 3, 1. Ooh, this point's far. This is 1, 2, 3 and a half. A half. 1, 2, 3. This one is about, oh, it's always those ones that get me. Those are always the tricky ones, the little negative ones. Here we go. Now, if y equals 3 to the x has a horizontal asymptote, then it would make sense that log base 3 of x would have a vertical asymptote, and it does. So that's the first thing you learn about log graphs. Well, first they're inverses, but secondly, they have a vertical asymptote. So this is log base 3 of x. This is 3 to the x. Good? Cool, okay. There's another way we could do this. So you have your pick here. Make a table for y equals 3 to the x. So that part isn't changing. Okay, so same table as before. But instead of graphing 3 to the x, we're going to switch the x and y columns. Remember, we could do that when we were doing inverses. If you had a column, two columns of values, you could just swap them for the inverse. So to have a table for log base 3 of x, I just take all of these y's and make them the x's. And I take all of these x's and I make them the y's. Just like that. And then I can just graph this one. But as you'll see, it's it's the same. So let's start with our middle one here. So 1, 0, 3, 1, 2, 9, over 1/3 down 1, over 1/9 down 2, over 1/27 down 3. But if you compare this to this graph, you'll see that it's the same. Don't forget your vertical asymptote. It's important that you draw that in there. So it's up to you which method you like better. Oops, I forgot to erase those. Okay, so let's take some notes about what we found about the log graphs so we can see them. So y equals log base 3 of x doesn't intersect the y-axis. So it has an asymptote of, I feel like I didn't write this right. Oh, no, I did. X equals 0. So that's a vertical asymptote. I'm just going to write that in there because I didn't before. Okay. Let's see what else. Y equals log base 3 of x has an x-intercept of, where's the x-intercept? Oh, I see it. At 1, 0. Okay. Just like the y-intercept of 3 to the x is 0, 1. Log base 3 of x has a domain of, well, it doesn't ever go past the y-axis, so it has to be bigger than 0. So 0 to infinity. And the range, well, it has arrows pointing over here, but this is up. I mean, it's slight, but it is going up. And this points down forever. So the range is all real numbers. So that's a basic log graph. And this is base 3, but no matter what the base is, none of these facts here would change regardless of what number that base was. We're not going to focus that much on log graphs because you work on them in great detail next year in pre-calculus. But you should, at the very least, understand that they are inverses of exponentials and that as scary as a log function might seem, you have all of the skills you need to graph it. But that's going to kind of be the end of our graphing of logs. You just, need to be able to produce a pretty generic one and kind of understand what it looks like. Okay, that's it for